Hello everyone and welcome back to another little video where I'm going to be expanding further into polar coordinates, and this time around I'll be talking about how to find area under polar curves. And I'll do so by first developing the machinery that we need to do this operation, and then I'll apply it to a couple of relevant examples below. Now, to talk about area, we must first find a way to calculate the area of chunks of a circular segment. And for that, I've incorporated a full circle here of some radius r. And I'm thinking right now how I can create basically an area segment, and the process itself looking like this. Taking my r vector here from the theta equals 0 position and moving it around. And as again, we open it up right now, we have an opening angle here, theta, that is growing. We basically create an area segment right now, whose area we can actually talk about. So again, this is the opening angle, and this is the area we're talking about. And this is still r, because again, this is the original r vector just moving around the circle. So what would the area, that's what we want to see here. Is there a relationship between the area of that segment and that angle that we've opened up? We can answer that question if we consider the limiting case here of taking this r and opening it up wide enough so that it goes all the way around. That would mean right now that we've incorporated the entire area of the circle. And that area we very well know is pi r squared. But how much did I have to open up this angle for this to occur? Quite obviously, I had to open it up by an amount 2 pi. So I create this simple little ratio here in order for me to solve again for the area that I'm going to create if I just simply opened a segment here of angle theta instead of the full circle. So I want to find this area again. So, it's a simple rearrangement operation here. We drop the pi's and we can take the theta on the other side to get ourselves here 1/2 r squared theta. And that's it, really. That's what you can use to find the area of any, again, segment, circular segment. So I take this notion now and I go and talk a little bit about a polar curve over here. So polar curves can look in weird and interesting shapes. I'll just put a random curve over here. That really doesn't matter what this function is. So we want to find again the area. Here's what we're going to do. We want to find the area between certain angles here in polar coordinates. So I'm going to give myself boundaries in terms of theta. So this might be, for example, theta equals, eyeballing this would be like 25, maybe 30 degrees. And that one up here would be 60 degrees, maybe 70 actually. Okay, so we give ourselves bounds in terms of theta because essentially we're going to be rotating in the xy plane as we do the integration. So how do I do the integration? Well, we got to take a little segment, break this down into very, very small segments like we usually do for our Cartesian curves. Okay, that's exactly what you see me doing here. And then I'm going to ask myself how much area does each of these segments basically create. You can see me here draw the first vector coming from the origin to hit the segment. I think though I have to make these segments a little bit bigger so that you can see them better in the video, because if I don't, they're going to look pretty messed up, the whole geometry that we're going to do. But you can understand that these segments are actually infinitesimals. They don't have almost any length. So again, we take a little vector here from the origin to the beginning of this little segment, and we do it again to the end of that little segment. And you will see a very interesting scenario start to build up and arise here. So technically, again, this is an infinitesimal, and these two vectors, if, again, this is an infinitesimal, you can see that they would converge basically to the same value of r. And that's the idea, right? You can see that they would converge to being the same length. I've opened them up, of course, so that we can see the geometry involved when that happens. Now, we understand here that Since we're talking about a very small change here in the curve, the opening angle that our r vector has done to move from here to that position up there, the opening angle that it has done, is going to be an infinitesimal as well. If this is ds, then the opening angle here will simply be d theta right now. And like we said, under the approximation that ds goes to 0, the value of these r's remains the same. So we have two r's over there, and we're seeking to find the area of this inner part over here. As you can see, I'm shading it in right now, called dA, because it's part of the entire curve. It's not the entire curve's area. And this dA, we can very well use our knowledge about circular cross-section areas and write it as 1/2, again, and then r squared. R, though, this time around is changing, and it is a function of theta. You can see, for example, that as I drag around this vector, for example, down to here, to that position, you can see how much longer it is when it tends to an element over there than what it is when it tends to an element here, right? It's changing with respect to theta, its length. Okay, and then of course we need to multiply by the opening angle that this ds has created here, and that angle is d theta. And really that's it. That is how we develop the area element for any polar coordinate function. And now we can take our information and actually go and apply it to a couple of examples, see how they play out. Okay, so we have over here a question that's asking us to determine the area under the following polar curves and between the indicated intervals. So the first one is sine of theta, and we want to go from 0 to pi to evaluate again that area. How we're going to start it off is, of course, when we turn this into an area, to turn it into an area, we have to integrate both sides, right? That's exactly what I'm doing here. So this is just A. So we have the area is equal to, right now, 1/2, and then the integral of r squared of theta, d theta. So who's telling us right now how r is changing with theta? Well, quite obviously, the function that we were given. So that's what's going to go in for that position. Okay. So we're going to have 1/2 right now, sine squared theta, essentially, d theta. And the bounds they've been kind enough to us to give us the bounds, and we go from 0 to pi for that. Now the question is how you integrate this. Well, typically, again, this sine squared I would treat with a double angle formula, the one that can immediately convert this into a cos 2 theta. And you can do the conversion as follows. So sine squared theta right now is exactly 1/2 plus 1/2 cos 2 theta. So we basically replaced the square problem with a function that we can actually integrate that's to the single power. And the bounds are still going from 0 to pi. Now, what you can do is factor here the 1/2s all the way outside to get yourself 1/2 times 1/2, which is 1/4, all the way outside though. Open a bracket, and then we're going to simply have the integral of d theta from 0 to pi right now as our first integral. And then we're going to have the integral of cos 2 theta plus here the integral of cos 2 theta d theta from 0 to pi as well. Okay, and then we can do antiderivatives here pretty easily. So we have basically here theta, and from the cos theta, where did it come from? If we think about the antiderivative, it must have came from a sine 2 theta. But if you differentiate the sine 2 theta, you would get a factor of 2 sitting outside here. So we want to divide this guy by 2 to make sure that doesn't happen. And if you take the derivative of this right now, quite obviously you're going to get that guy. So we're good to go. And we're evaluating this from 0 to pi. So again, we're going to put in our values for the integrand. We've got pi plus sine of 2 pi over 2. And then we would be taking away basically 0 plus sine of 0 over 2. Now, both terms in the second part here, when we did this evaluation, they go to 0 because sine of 0 obviously here is 0. But sine of 2 pi is also 0. So the only thing that remains is actually the pi, and that's what we get back. We get pi over 4 as our final answer. And that's the end of this example. So, moving along now, with this, I guess, here version of our formula, not this one, we can attack the second problem in a similar fashion. Make sure, again, that you're very familiar with at least some trig identities when you're attempting polar coordinate questions and integrals. So again, over here, who is the guy that talks about how r changes with respect to theta? It is the function that you're going to be integrating, of course. So we're going to put that in. We're going to have here sine theta plus cos theta squared. And we're going to be taking that integral from 0 to 90 degrees, or pi over 2 radians. Okay, so the best way to do this right now, I guess here maybe a version of use substitution would work. But I'm going to go ahead and expand because I can see something better. So if I expand the bracket right now, I will get myself 3 terms: a sine squared theta, a 2 sine theta cos theta, and a cos squared theta. And before I move on, before I distribute any of the integration in here, I'm just going to take care of what each of these things is going to be using trig identities. So let's see over here. For the sine squared, what can we do? We said previously that we can replace it with 1/2 plus 1/2 cos 2 theta. Well, what about the cos squared? In a very similar way, you can actually replace this guy with 1/2 minus 1/2 cos 2 theta. Interesting. And then the middle one here, the middle guy, it's literally nothing else other than sine of 2 theta. This is the double angle formula for sine 2 theta. So you can see here that I can open up a big bracket and then start putting all these things in here. We're going to get a little bit of cancellation, as you can see, for the cosines. So we have 1/2 plus 1/2 cos 2 theta plus sine 2 theta plus 1/2 minus 1/2 cos 2 theta, and then all of that being integrated. Okay, so these are going to go away. These are going to add to 1. So we basically have 2 integrals right now remaining. If you can see here, we have the 1/2 sitting on the very outside, and now the integral being distributed. 1/2 plus 1/2 gives us 1. So we have d theta, essentially, going from 0 to pi over 2. And then we have the sine 2 theta being added here, the integral of that, between the same bounds. The cosine terms have canceled. Okay, so moving on, the integral of d theta, obviously just theta. And the integral of sine 2 theta, we just did that. It's going to be over here. Actually, we didn't just do that over here. We did the integral of cos 2 theta in the previous example. This guy here must have came from a negative cosine 2 theta. But again, if I differentiate this, I would pop out a factor of 2 here that I don't like. So I'd have to divide this by 2. Differentiating this now would give us exactly this. So essentially here, I can combine these to give me here a negative sign. So negative cos 2 theta over 2. And we're evaluating these again from 0 to pi over 2. Now it's time we plug in the bounds, and we get ourselves 1/2 pi over 2 for the first bound in the first position, minus cos of pi divided by 2. Okay, and then we take away 0 as this comes in, and then minus cos of 0 over 2. Okay, I think this is all good. let's take a look. Cos of pi here is essentially -1. There's a double negation here. And then cos of 0 is 1. So when we unleash everything here, we have pi over 2 plus 1/2, and then plus 1/2 again from what it looks like here. Double negation. Okay. So let me make sure. Yep, 1/2 plus 1/2, that's what it looks like. And so we end up getting ourselves here pi over 2 plus 1 over 2. And I would leave that there. You can evaluate that in your calculator, but again, it's no need here to do that for this video. So again, these are two examples and how they are done in polar coordinates. I hope again the development of the formula was easy to follow and that it's been helpful. If you found this informative and helpful, consider subscribing. And again, thanks for watching.